Alright, so given how long the last couple videos have been, well, I mean the second last one, I went way over time. I kind of expected to go short on the last one and then I didn't. So I'm going to aim to go short over this one. Today we're covering Engel's theorem. I don't think it's going to be enough for a normal video, but like I said, I want to make this video go kind of short, so I'm going to cover it a bit slow on purpose here. So, what is Engel's theorem? Well, we have a lemma. I'm going to let V be, V be a vector space over K, which is our field. Then, if X is a nilpotent endomorphism, that is, it's nilpotent in the sense, keep in mind that X is a map of V onto itself. And so it's going to be nilpotent in the sense that iterating that map a finite number of times is going to end up bottoming out to be the zero map. Then the mapping of Y to the Lie bracket of X and Y. So this is essentially just the adjoint representation of X of linear maps of V to linear maps of V is nilpotent. Essentially, we can do this. We can take the adjoint of X on Y only finitely many times before it zeroes out. Now we note if F denotes, not donates, if F denotes this mapping, then our iterate fm of Y is a sum of terms of the form positive, negative, x to the I times y times x to the j, with I plus j equals m. If, keep in mind, x is nilpotent, so x to the k equals 0 for some k, then f of 2k minus 1 y then essentially we have to have at least xi or xj be k, which is sends to 0, so this map is 0 for all y in LV. This is our proof. Now let's look at Engel's theorem, as you would expect from a video on Engel's theorem. we're going to let V be a vector space over K. And G a finite, sorry, 1 second. Probably hear me trying to open my water bottle one-handed there. And G a finite dimensional subalgebra of the general linear Lie algebra of V. So G itself is a Lie algebra whose elements are nilpotent endomorphisms of V. Nilpotent endomorphisms of V. If V is non-trivial, there exists U non-trivial in V such that the action of X on U is equal to 0 for all X in our G. What's the proof? The proof is by induction on N, which we're going to set equal to the dimension of G. And keep in mind that because everything you'd want to be linear here is linear, it's essentially going to act dimension by dimension. Once again, if the dimension of G is 0, then its only element is 0, which means you can take any non-zero U, and since X has to be the 0 map, that works out just fine for the case. So we only need to think about the case when N is greater than the 0. So we're going to let H be a Lie subalgebra of G with the dimension of H being equal to some element, some value m less than n. If X is an H, and the adjoint in G of X maps H onto itself and defines on passing to quotient an endomorphism sigma of x of the space G over H. So I guess sigma of x is, sigma of x is the quotient of the map of the adjoint representation of x on G to G over H. By our lemma from above, the adjoint of x is nilpotent, and hence so is sigma of x. From the induction hypothesis, there exists a non-zero element of G over H which is annihilated by our map of sigma of x, since we have the Engel's theorem by induction. For all x in H. Thus H is an ideal in some m+1 dimensional subalgebra of G. Thus, we see that G has an ideal H of dimension n-1. So we're going to let A in G but not in H. Okay, I guess I should write let H in G be an ideal of dimension n-1 with alpha in G minus H. So alpha is A is essentially, I guess not alpha, A is a point along our new dimension, if you know what I mean. Then once again, by the induction hypothesis, the U in V such that the action of x on U equals 0 for all x in H, which we have by induction hypothesis, form a non-zero vector subspace of U. There's a vector subspace which we're calling u, sorry, of V. Which is stable under A, which is something we proved from before. Now, since that A is a nilpotent endomorphism of V, nilpotent endomorphism of V there exists a non-zero element of U annihilated by A, and hence, and because, as we saw, A is kind of represents a new dimension in that any element of G can be represented as the sum of an element in H and a linear multiple of A, then this has to be annihilated by all of G. Now that is Engel's theorem, but we have 3 corollaries which we want to show. So, Lie algebra, first corollary, algebra G is nilpotent if, I guess I should be writing all of this out explicitly because we're taking things slow. That's what it means to take things slow, is to rewrite everything. The algebra G is nilpotent if and only if, so essentially this is another alternative definition of nilpotency for G, if and only if the G adjoint of X is nilpotent for all X in G. Now, if you recall from our original discussion of equivalent definitions of nilpotency, we saw that it means that there's some finite value k for which the chaining of k adjoint representations for any k elements is 0. And so that of course implies that for any x in G, the adjoint representation adjoint of x as rated k times is 0. So we have that that if it's nilpotent, then that the H adjoint of X is nilpotent. But the thing is, we don't get the other direction for free, because we have to say that the chaining of any n adjoints is 0, and we don't know that yet. All we know is that the chaining of any adjoint representation with itself n times is 0. So we only need to prove this way, and we're only proving this way, and we prove by induction. That's a terrible arrow. induction on n equals the dimension of G. Of course, once again, the zero-dimensional case is trivial. So we're going to have G be our n-dimensional Lie algebra. So just a reminder of our setup. G is an n-dimensional Lie algebra with every adjoint representation of every atom in G being nilpotent. And we know that this we have this corollary for degree less than n. We see by the set of the adjoint representations of X that the center of G is non-zero. I guess I should spell it fancy just for the sake of it. Of G is non-zero. And then G is a central extension of G over its center, which is a Lie algebra, which is nilpotent by the induction hypothesis. And we showed that that is enough to show that it is nilpotent. So that's actually the entire proof. And just keep in mind that the center is non-zero essentially because we know that the adjoint of X to the sum n has to be equal to 0. So there you go. Second corollary. Corollary 2. Where is my mouse? Let G be a Lie algebra with ideal H. Suppose that G over H is nilpotent and that for all X in G, that the restriction of the G adjoint of X to H is nilpotent. Then G is nilpotent. The proof of this is pretty straightforward. Once again, let X be in G. And since we have that G over H is nilpotent by assumption, there exists a K we have a k such that the adjoint representation of x, k times this on G over H is 0, which is equivalent to saying that this on G is contained within H. Likewise, we have a k prime such that adjoint representation x of k to the k prime of H is equal to 0. Hence, we can then compose adjoint. This is going to act. Adjoint of x is going to be acting on G. Doing it k times sends it to H. And doing it another k prime time sends it to 0. Thus, every element is nilpotent. Thus, the algebra itself is nilpotent. We have one last corollary, which they don't really bother proving. So we have V be a vector space and G a finite dimensional subalgebra, finite dimensional subalgebra of our general linear Lie algebra of V, whose elements are nilpotent and the morphisms of V. Then G is nilpotent as a Lie algebra. And yeah, it's easy to see why they didn't bother proving this. We've seen this already, given just what we have. Everything is nilpotent, all of our adjoints, and so everything is, yeah. And I feel like I said, a bit of a shorter episode, not even quite half an hour. But given that we went like half an hour overtime, I think this is fine. Hopefully. It's nice having like the entire video laser focused to like one chapter, especially when you can't take an easier approach to that chapter. Depending on how we go, there might only be one more video on nilpotent algebras directly, at least from this source, so that's something.